So we just moved our dates.
Morning, Chow. I'm fine.
Other than that.
I was going to harass you about coming in and interrupting class, but I don't think it goes over well.
Yeah, that's what me and you guys do.
Because class just doesn't begin until both of you show up?
Yes.
All right, so once again, I ask, are there any questions? You do have a quiz on Friday.
What the quiz was today?
What's what?
What the quiz was today?
There was should have an email sent out that would have pushed it off. So you get to sit back and relax for the next couple of days because you're prepared. Yes, quiz is Friday, not today.
Does the master set still do Friday?
What I have is everything basically got pushed off a day.
Cool.
So the current schedule is 2/28. We have the quiz on 20. This is Friday. Monday. And then on March 2nd, master set on 20. And March 6th, the quiz on 21. And then 3/9, master set on 21. And the intent is I'll post solutions for this after class, so no late. And on 3/11, test 1B. And we don't miss class the week of spring break.
It starts on
It is
Tuesday.
Tuesday,
Thursday.
Yeah.
I just missed one.
They ignored the,
Yeah.
they did this a couple of years ago, and I was told that they realized it was a mistake and they would try desperately never to do it again.
I decided to do it again.
Yeah, you know, you forget. Those who do not remember history are doomed to repeat it.
That's why you write things down,
Yes.
and why we have history classes.
Literally self-learners.
Yes.
I would not be here for the test because I wasn't teaching busy.
I guess your test will be easy to grade then. We should probably talk about, you know, that one-on-one.
I'll take it the next day.
The next day.
Yeah.
Actually, probably do.
All right. So that's what I have written down. Just don't tell Brenda. All right, in the absence of other questions. I don't know how well this can be seen on the video that will eventually get posted, but there it is, so.
The quiz on the 20th, yeah, the master set.
I'm about to erase this. All right, so if there's a desperate need to do the quiz today, we could.
No, that's good.
I could go print it off. I know some of you are prepared. I apologize for the last moment change. If we ever miss a class day, then do please look for an email. And we are into the third section now, of course. Magnets.
So this is, what chapter is this?
22. So this is the first material on the, what has traditionally been the last task. doesn't quite seem balanced right. You know, you feel like the first quarter of the course is on a test, and the second quarter is on a test, and then the last half is on a test. Maybe to make it fair, we should just have one test at the very end to cover everything. All right, so what can you tell me about magnets?
They
The
hold
Earth,
things together.
Okay, pardon?
the Earth is a giant magnet.
Okay,
They can repel.
okay.
Be repelled from one another.
Should we say opposite, right?
Opposite of what?
Uh,
I figured this was going to be one of the first things people said, but let's drag it out of you. Pardon?
the charges, or
The poles.
poles, sorry, there it is.
Ah.
There you go.
Poles, huh? Do we have names for these poles?
North and south.
Yeah, okay. So they have a north and south pole. It is not a positive and negative pole. Now, there are some theorists who do come up with a magnetic charge, but it's purely theory. At least as far as the stuff I've ever gotten into. North and south poles, and then opposites attract. Like repels. What else? Oh, and Earth is a magnet. All right, so this is the Earth. We'll go with the traditional. We are here.
Yes. Forget about Canada.
All right, from a magnetic point of view. From a magnetic point of view, where is the North Pole of the magnet that the Earth produces?
It's like slightly off from the tilt of the Earth.
No.
No.
The very top.
No.
You mean
Very
magnetic?
nice.
Wait, do you mean magnetism?
I'm talking about as the Earth, Sarah earlier said the Earth is a magnet.
Right.
And the question I'm asking is, where is, if you think of the Earth as a magnet, where's the North Pole of the Earth's magnet?
The very bottom.
Very bottom, or probably slightly off.
Yeah. Magnetic Earth is like slowly moving.
It is, and from geologic time, it's expected any time now it's going to flip, which means sometime in the next 100,000 years. But the reason why we call this the North Pole is that the north end of our magnets point in that direction. But north ends of magnets are attracted to the south end of magnets. So from an Earth's point of view, this is the south, and this is the north pole and pole, even though we call this the North Pole. So this is from a physics point of view, and this is from a geography point of view.
That's very frustrating.
Yes, it would be nice if they had come up with some sort of system that worked better, but you know, like electrons being negative and protons being positive, this was established before they knew what was going on. All right, so what's an electric field? And the silence explains some of the answers I saw on the test.
It's like the field that emanates from a point charge.
Okay, I'll go with the spirit of that. If I have a positive charge, which way does it go?
Out.
And if it's a negative charge?
Inwards.
All right. Well, poles do the exact same thing. They have these things called magnetic fields. And as you would expect, the symbol for a magnetic field is the capital B.
Of course.
Now, there are some textbooks have a different thing. They call B the magnetic field density. I forget the exact wording. And then H is used for the magnetic field. But that, I've only seen that in more advanced textbooks. Almost every other textbook that you are going to see, unless you really pursue physics hard enough, this is what they're calling the magnetic field. Why B? I think it comes down to when they were creating, whoever came up with it, the first one used the letter A, then B for the second thing, C for the next thing, and B stuck. So when we talk about magnetic flux, which we will at some point, sometimes I'll put a B down here, and sometimes I will do an M for magnetic flux. And the magnetic field, external to the magnet, goes from north to south. So if I have a magnet here with a north pole and a south pole, I expect the magnetic field lines are coming out the top. That's not what I want. My arrows here. And into the south. And you draw these until you get tired of drawing. And there you have a beautiful magnetic field drawing. Internal to the magnet, what would you expect?
South to north.
And it is continuous. So this one coming in will eventually go all the way through, that one will go all the way through, this one will hit one of these things, is that one. And so we have this continuous magnetic field going in, magnetic field going out. Matter of fact, if I take any closed surface, I have as much magnetic field going in as I do going out. So when we talk about electric field, through a closed surface, that's going to be equal to the enclosed charge divided by epsilon sub naught. But if we're talking about the magnetic flux through a closed surface, that's equal to 0. Now, this whole idea of magnetic fields, I'm sort of asking you to believe, to give a little bit of physical evidence that this might actually exist. Give people a last moment to write stuff down before I will cover it. Hopefully that's close enough.
Yes.
All right, so what I have here is, this is some sort of oil in here, and it's slowly leaking out, so there's going to be an air level in it. There are the little black stuff right here, are little iron filings. And so if I shake this, the iron filings basically get distributed throughout, and it's going to hang there for a while. Eventually, gravity will take effect, and all of the little filings will sink back to the bottom. So I'll put this on here. That's good enough. And then classic focusing. There we go. And you can see the giant. All right, so I'm going to take a magnet. right, so it's already marked north end, south end, so I know which one's which. And so north end is going to be, I guess from your point of view, down here. Let's see, shift it. And you can see, start to see the iron filings sort of start to move. Now this definitely is not proof, because science doesn't offer proof, it offers support. But there does seem to be something going on. As you can see that the filings seem to be lining up, and there seems to be a general trend going on like that. Those are the magnetic field lines. Since the north end's down here, what you're seeing is it going from this point to the south end over here. Also notice, it is never nice and neat as it is on the board. On the board, we always have it going out the ends, at least that I do, going out the ends. But you can see it's sort of clustering on the sides here, not just straight out the ends. You can also see the effect of the magnetic field as it's sort of trenching out like that and officially going around that way. Now I have another magnet here. And if I add that to it, should start shifting some more. Now in a nice, beautiful, ideal board case, you would not get the clustering right here. All we would do is just the extending the magnet. But you do notice that we do have this trend coming over here, magnetic field lines going along like this. And there's a little bit of clustering right here because we basically just have two magnets. You can look at it a slightly different way. Any questions before I take this one off? And you'll start to see the iron filings starting to reshift again and basically get moved around by currents and basically fall. All right, so we have, it's a bunch of iron bars. There should be no particular order. We can shake it. I've given it an order, so we can go that way. That's somewhat random. And we'll take the magnet again. And we immediately see the lining up as it goes to this north end down here, and you can start to see it come out. Notice that this is not particularly affected right here because the magnetic field weakens the farther away that you get, as you would expect. I can say as you would expect. I'm assuming everybody here has played with magnets at some point in their life. You know that two magnets this far apart are not particularly attracted to each other. It's not that they're repelled, it's not really close that magnets become fun. And then I can take the second magnet, attach it to it. And again, we see the same thing that we saw before. We got a little bit of sort of curving in at the junction right here, but for the most part, it's coming out like that and around into the north pole, or south pole there. Questions? And then another one that I haven't done on this is a different kind of magnet. This is primarily for a demonstration that we'll do later. But I have a north and south pole, and what happens when I stick this in here? We have a magnetic monopole. Nobel Prize, right here. Why does it not seem to be curving around? Yeah. And so we should see it if we put this thing on its side. And notice that I shake it around a little bit, give them a chance to align themselves. We are seeing, it's a smaller magnet, but we are seeing an effect as we further out that they do seem to be sort of spoked towards this, although those seem to be an exception right there. Oh, that's because it's going, I don't know what side's north and what's the south, but we can test that out. All you need to know is one, and then the rest come in. All right, so south end, north end. So north is at top this time. And you see the going from north. Or you see something there, and I'm telling you it's going from the south and magnet. All right, questions? And for some of you, it was a flashback. And yeah, it's still on screen. Ooh. There's nothing one. Oh, wait, this is the one. All right, so let's talk units, because everybody loves units. And the evidence that everybody loves units is that some people on tests will just write down random units, just because they love them so much they thought, we haven't used this unit in a while, let's just put this one in. All right, so the units of a magnetic field are Teslas. This is the SI unit. Oftentimes with magnetic fields, especially the more advanced physics you get, you tend not to see that. The CGS system, the centimeter gram second system, as opposed to an MKS, is the Gauss, which is a capital G, which is GA.
And this is in the what system?
Pardon?
This is in the what system?
CGS system. It's the metric system based upon centimeters and grams and seconds, as opposed to kilograms, meters, and seconds.
Do we ever use this? Gauss?
Yeah, we will use Gauss occasionally. The reason why Gauss exists, it's similar to the fact that water, the specific heat of water is 1 in a particular unit system. Density of water is 1 in a particular unit system. I mean, water is sort of universal, and so you pick that as sort of your base. So Gauss is similar in that respect, in the fact that the magnetic field of the Earth, it varies, but it's approximately a half a Gauss. And again, GA or G. And apparently, I don't have that written down there for some reason. That's
G, sometimes GS.
GA.
Sorry, Dr. Gibbons, sometimes G.
Oh, sometimes GS? Okay, thank you very much.
That's usually G.
Then we'll just go with G. Now, the magnetic field of the Earth does vary. It's not like, I talked about the fact that we have the Earth here with the South and North Pole. And so the magnetic field lines ideally are going to be doing this. This is the ideal. In reality, it's not this nice, beautiful magnet the way I tend to draw it on the board. So, but the general tendency is that it's in that direction. Thus, magnets, the north end of a magnet will point in, assuming there's not enough other forces affecting it, will point towards the geographic North Pole. Some call it the magnetic North Pole, but in reality, magnetic South Pole at the top of the world. And yes, I am using a northern hemisphere type of view when I talk about that. I will always, in terms of this class, just at the convention, I will always draw the world so that we are on the upper half of the world. I taught in South America, I might be flipping that, but I'm not there, so I'm not. All right. Also, in terms of unit, electric flux, what's the formula? Oh, sorry, wrong symbol. Electric flux, not a vector.
Something, E times A.
Say it again.
E times A.
Magnetic flux,
E times A.
so if we looked at the units here, the units of magnetic flux would be a Tesla meter squared. Just like up here, the units of electric flux would be a Newton per Coulomb meter squared, or Newton meter squared per Coulomb. Down here, Tesla meter squared, and it's fewer letters than what we had for electric flux. However, this was too much for people to write. So this is a Weber. Even though there's only one D, it's pronounced, at least I've always heard it pronounced Weber.
It's the same amount of letters.
Say it again?
It's the same amount of letters. It's 2, 10. Whatever.
Yeah, well, apparently Tesla meter squared was just too much to write. Well, you do have the dot, don't forget there's the dot there. Because without the dot, it would be parameter squared, which is a really huge area. Ah, there's part of my problem. I'm in the wrong section. To give you also some idea of strength here, in terms of these two systems, 10 to the negative 4th Tesla is equal to a Gauss. Typical lab magnet. B is in the order of 2. Just saw it. 2.5 Tesla. And then the superconducting magnet, the big ones, the multi-million-dollar magnets, superconducting magnet is in the order of 30 Tesla. So again, to give you some idea of size, so if I do a problem and I say you got 100 Tesla magnet, just realize that's unrealistic.
Will we play with magnets?
Will we play with magnets? We will do something with magnets. I'm not sure it's called play. Well, all physics is just play, so.
Because physics is fun.
That's right. All right, any questions before we bring back, since we're doing Flashback Monday, bring back some other fond memories?
Have you ever played with those little buckyball things
I have not.
that like go to students? I have a set.
Ooh, nice.
My uncle had to buy them from like not in the United States because apparently you're not allowed to like ship them in the United States. Really?
So your uncle's on a number of watch lists, and this is not videotaped, so she's just joking for anyone watching this video. I have no idea if it's illegal or not. Presumably customs would have nailed it. It's not like, if it's a magnet, presumably it would have been picked up. It's like students who hypothetically in the past have gotten the sort of European version of the textbooks. which is identical to this one, except it costs half the price. I assume the person who sold it broke the law, not the person who bought it. Hypothetically speaking.
Of course.
All right, now, forces. Ultimately, we got to get back to forces. We had a nice little formula dealing with forces between two charges. And with magnetic fields and magnets, we don't have a nice little formula. What we have are various situations and various formulas. So there was one semester I got so fed up with, here's the situation, here's the formula, here's the situation, here's the formula. It's a little bit smoother than that now, but there is a certain amount of, you do need to know which formula goes with what situation. So I'm going to write up a formula. And based upon the letters used here, what would you guess this formula is saying? All right, Denise, you got the first part.
Force equals,
Ma.
I guess charge times velocity times the magnetic field.
Yeah, so therefore the force, conceptually, what are we saying then? I mean, you basically, that's what the letters mean.
The force varies dependent on the charge and the velocity of the
Magnetic
magnetic
field.
field.
I was gonna say like the charge is like the mass and the cross product of the velocity and magnetic.
Wait, did you bring the word mass in?
But I think it was in there.
Okay, so you want to go ahead and set this equal to MA?
Yeah, and then just Q equals M and then
Oh, you're paralleling like that. No, you can set it equal to MA because if that's the total force, that's equal to mass times acceleration. I'll buy that one, but yeah, I'm not looking for a parallel.
okay.
All right, so this is the force on what?
Charge.
Yeah, this is a force on a charge. And what is this charge doing?
Moving
Where?
through a magnetic field.
Now, the flashback is that cross product. How do you do cross products?